All right, good morning, everybody. Um, as I mentioned, this is an asynchronous day for the most part, but one thing I wanted to touch on really briefly, there was a lab that we normally would do in a non-COVID environment. It's called the Balloon Rocket Lab. And what we did is we used latex balloons. We started them from one side of the room, and we launched them on a string, and we had them travel to the other side of the room and come back without the students touching them. So you're blowing up balloons, and there's spit flying, and they would explode, and whatever. It's kind of dirty and gross a little bit in some respects, but in a normal year it was just kind of icky. But this year we obviously wisely opted to not do that lab. But I want to talk about the physics behind it because I think it's relevant. So you have your latex balloon like this. And the question I ask is, what is necessary for this balloon to travel? Is it necessary, these are air molecules, in case you couldn't recognize them, is it necessary for there to be an atmosphere, in other words, for there to be air in the room to push against in order for the balloon to travel to the right? I then use an example like, if I push, I'm sitting on my chair, if I push without touching the wall, I don't do anything. But if I push and touch the wall, then I move. So I need that wall to push against in order for me to move on my chair. Is the same rationale true? Does there need to be an atmosphere for this balloon to push against in order for it to travel to the right? And so we talk about it a little bit and get some feedback from some students. And I said, if you're okay with saying that we need to have this atmosphere, then you need to also be okay with rockets in outer space not being able to propel themselves. Now, you probably know once a rocket is in outer space beyond Earth's atmosphere, it doesn't need to propel itself anymore. There's nothing to slow it down. Objects in motion will tend to stay in motion. But if it wants to change its trajectory and has these little jet rocket propellers and what are stabilizers and whatnot, small little rockets to change its path, it fires them off, and it doesn't need an atmosphere to push against, because the physics behind what causes a rocket to be propelled is exactly the same as it takes for this balloon to be propelled. If this was a rocket engine, the engine takes this fuel, burns it, and throws it out of the back of the rocket engine. And then the reaction is the fuel then pushes the rocket forward. So fuel goes this way, rocket goes this way. In the balloon rocket, this elasticity of this balloon forces the air out the back. That's the action. And the reaction is the air pushes the balloon forward. So balloon throws air, air throws balloon. It's the exact same concept. A rocket, rocket throws fuel, fuel throws rocket. Those are the action-reaction pairs. And what we did in the lab is we would tape a little straw to the top of the balloon, and then we would guide this.
Steve Banks, call 58101. Steve Banks, 58101.
We would guide that along a string, and that would be the way that we would travel from one side of the room to the other side of the room. So anyways, I just wanted to share that with you. Remember, when we're doing action-reaction pairs, that they always occur in pairs. And so don't ever include a third object. It's balloon throws air, air throws balloon. Just for a quick example, there's a question in your homework. If you push on a refrigerator with a force of, let's say, 100 newtons, and it slides across the floor of your kitchen at a constant speed. Okay? Well, then you know automatically that there is 100 newtons of friction force between the refrigerator and the floor, because it's moving at a constant speed, and then that force has to be 0. So the question is this 100 newtons equal to this 100 newtons? Well, obviously yes, 100 is equal to 100. Is it in the opposite direction as that? Yes, it is. Is this the reaction to that action? And the answer is no, it is not. The reaction to you pushing on the refrigerator is the refrigerator pushing back on you with 100 newtons. You, refrigerator, you. If you were saying you push refrigerator slides on floor, that's 3 objects. And you have to have only pairs to have an accurate action-reaction pair. So there is another action-reaction pair here with the refrigerator and the floor. But that's not what the question was asking. Is this reaction the reaction to your pushing against the refrigerator? And it's not. So anyways, just keep in mind action-reaction pairs occur in pairs, just 2 objects. So, all right, so you have some activities, you have some couple of review problems I put in the outline for the day today, similar to what we did on Thursday. I gave a couple of suggestions for some concept builders for you to play with. I posted some quizzes for you to try, Chapter 6 quiz, Chapter 7 quiz, to kind of assess your understanding. Maybe you want to do that maybe later this weekend. But anyways, that's all I got. Have a good day. And if you need anything, don't hesitate to send me a message. All right. Take care.